and from orbit. Tyndall Glacier looks as if it is being pulled apart at the edge of a dark Patagonian lake, with white fractures crossing the lower ice in every direction. Beyond the front, dozens of icebergs drift through Lago Giki, marking places where the glacier ended only moments, months, or years before, and the newest view came from an astronaut aboard the International Space Station on May 10, 2026. It captured a glacier that had already lost about 2.2 kilometers of length since November 2022. The change was not hidden inside a chart, and it was floating in the lake as a field of newly detached ice. The lake remembers. The evidence is current. That is the first answer. Tyndall is still retreating, and the lake at its front is growing as ice gives way. But the harder question is what happens next? A calving glacier does not shrink like an ice cube left on a table because it flows, bends, and cracks while pressing forward under its own weight even as its surface melts and its front breaks away. The result can look contradictory. Ice moves toward the lake while the edge of the glacier moves backward. At Tyndall, the moving edge rises roughly 30 to 40 meters above the lake. Beneath the water, the ice continues downward toward a bed that is hundreds of meters deep in places. Every visible fracture near the front is part of a three-dimensional structure that scientists can only partly see. Stay with that image because the height of the cliff is not the most important measurement, and the shape of the hidden valley below it may decide whether retreat remains incremental or reorganizes into something faster. If you value documentaries that separate a real physical warning from an invented prediction, subscribe and stay with us. The next answer in this story is not found in the ice cliff alone. It is found beneath the lake, where the geometry of the valley controls how much resistance the front retains. Tyndall sits in southern Chile, inside Torres del Paine National Park, at the southern end of the southern Patagonian ice field. And that ice field is the largest expanse of ice in the southern hemisphere outside Antarctica. It feeds many outlet glaciers, some ending in the ocean and others, like Tyndall, ending in freshwater lakes. Lago Geki itself is a product of retreat, having begun to form around 1940 as Tyndall pulled away from an earlier position. As the glacier moved inland, open water occupied the space that ice had filled, and the lake did not invade a stable glacier from somewhere else. In other words, the glacier created room for the lake by withdrawing from the valley it once occupied. And that distinction matters because a growing proglacial lake can become both a record of past loss and an active part of future change. Water reaches the ice face while buoyancy reduces the force holding some sections to the bed. Waves and temperature differences can work against the submerged front. When the geometry is favorable, large pieces can detach with little warning. But Tyndall is not following a simple countdown to one giant collapse. During March and April 2023, satellites observed major calving events that helped produce a sharp episode of retreat. In the austral autumn of 2026, calving was active again, but it was more incremental. The lower glacier was so heavily crevassed that it tended to produce many smaller icebergs rather than a few enormous flat slabs, and that pattern is expected to continue, because the fractured appearance of the front led glaciologist Maury Pelto to anticipate many more small icebergs and another burst of iceberg production in the next austral autumn. Unexpected does not mean scheduled, and a satellite image cannot provide the date and size of the next break. It can reveal the physical setup: a tall front, deep fractures, open water, and a glacier that has recently retreated faster than it did during the quieter decade before 2022. This is why one photograph can hold two different stories. And the first story is dramatic and immediate, with a glacier breaking into a lake and leaving the trail of bergs visible from space. The second is slower and more consequential. Tyndall has been shrinking for roughly a century and a half, and the lake has expanded along the path of that retreat. Each new section of exposed water changes the boundary conditions at the front. Yet whether that change produces steady retreat or sudden acceleration depends on the terrain hidden below. Researchers have measured Lago Geki to depths of roughly 350 meters, and with later mapping indicating water near the retreating front deepening from about 308 to 420 meters after 2010. Those are not decorative numbers because they help reveal how much of the glacier may be supported by rock, how much may approach flotation, and where the front may lose resistance. Tyndall has crossed deep water before without becoming the fastest retreating glacier in Patagonia. That is the critical exception. Deep water can destabilize a calving front, but depth alone does not dictate the outcome. Depth is not destiny. The photograph also captures why remote sensing is essential here. Tyndall is surrounded by steep mountains, unstable ice, and fast-changing weather. Field teams cannot stand at the calving front every day, and clouds often erase the view from ordinary optical satellites. And when a clear image arrives, researchers can compare fracture lines, iceberg fields, shadows, and the exact outline of the terminus against earlier observations. One image does not settle the future, but it can show whether the physical setup is becoming more or less favorable for continued breakage. That comparison is especially important now because the recent retreat followed years in which the front changed more slowly. The glacier did not begin shrinking in 2022, although the pace and style of loss became newly visible after that date and gave scientists a sharper baseline for comparison. The next question is therefore more precise than asking whether the glacier will keep shrinking. It almost certainly will under the conditions already observed. So the real question is how that retreat will unfold. Will the front continue its pattern of advance, fracture, and seasonal calving? Will it encounter a section of bedrock that temporarily slows the retreat? Or will thinning and buoyancy remove enough resistance for a larger reorganization, and the rock is still hidden? To understand those possibilities, we have to leave the visible icebergs behind and descend into the shape of a submerged valley carved by the glacier itself. The Lago-Gaiki is not simply water beside the glacier, it occupies a valley that the glacier excavated while flowing through Patagonia. That valley contains deep basins, narrower sections, and changes in slope that can act like hidden controls on the ice front. And picture the glacier as a river made of slow-moving ice. Gravity pulls it downhill from the high ice field, while snow added upstream is compressed into ice that deforms and slides toward lower elevations. Near the terminus, Tyndall moves at roughly 500 meters. Tyndall moves at roughly 500 meters per year. The front may appear stationary for a time, but the ice inside it is continually arriving, and for the edge to remain in the same place, the arriving ice must be balanced by melting and calving, so the front can advance when more ice arrives than is removed. And if calving and melting remove more than the flow delivers, the front retreats. Tyndall often advances and retreats within the same cycle as dense satellite mapping has shown the front advancing for 1 or 2 years, then losing ground during occasional summer calving, and a single image of icebergs can therefore be real without representing a permanent acceleration. Scientists need a sequence of images to distinguish a dramatic episode from a change in the glacier's underlying behavior. Between 2020 and 2021, Tyndall retreated at an average rate close to 80 meters per year. The front moved in steps, and the retreat was not smooth, because large tabular icebergs appeared during episodic events, including in 2001 and 2010. Over the same 2 decades, the lower glacier surface dropped by about 153 meters, and that thinning changes more than the view from above, because ice resting on bedrock is resisted by friction and by the shape of the valley. As the glacier thins, the downward pressure at the bed decreases. Where the water is deep enough, buoyancy pushes upward against the ice. If a section approaches flotation, the effective pressure holding it to the bed becomes smaller, and the front can become easier to lift, flex, fracture, or detach. And this is one reason lake depth matters. Researchers surveying Lago Giki found a U-shaped basin reaching hundreds of meters below the surface. As the terminus retreated after 2010, it entered water that gradually deepened from roughly 310, and calculations for several earlier years indicated that parts of the front were near floating or even slightly superbuoyant. At other Patagonian glaciers, that kind of geometry has preceded rapid acceleration. When a front loses contact with a stabilizing high point on the bed, resistance can fall. And faster flow delivers more ice to the front, but it can also stretch and thin the glacier, increasing fracture and calving. Retreat then becomes dynamic, driven not only by surface melting, but by the glacier's own changing motion, and this is the mechanism behind some of Patagonia's most abrupt glacial losses. And yet Tyndall did not respond exactly like its neighbors. Even when calculations suggested near flotation conditions, researchers did not observe the strong acceleration seen at glaciers such as Uppsala Vigma, and Tyndall flows more slowly, and its lake is smaller, narrower, and generally shallower than the huge basins in front of those glaciers. Those differences appear to reduce the strength of the buoyancy-driven feedback. So the same ingredient can produce different outcomes. Deep water does not automatically create runaway retreat, and a near-floating front does not guarantee sudden collapse. Geometry decides the response, and the response depends on ice thickness, flow speed, fracture pattern, valley width, bed slope, and whether the glacier remains connected to points that provide resistance. That is why the phrase breaking into a growing lake must be understood physically, not theatrically. And the lake is growing because the front has retreated, and the water then interacts with the newly exposed face, but the lake is not a single switch that turns retreat on. And Tyndall's longer history reinforces that point, because NASA compared images from 1990 and 2007 and found substantial retreat over those 17 years. Earlier field measurements showed retreat rates around 80 meters per year from 1986 to 2000, increasing to about 135 meters per year from 2000 to 2011. And then came roughly a decade of more limited retreat, even as thinning continued before the major losses after late 2022. The pattern is uneven, and the glacier can therefore change its pace without changing its long-term direction. One eastern branch once terminated in Lago Tyndall, as well as the main front in Lago Gaiki. By 2010, thinning had severed that eastern outlet, which was a reorganization of the glacier's shape, not merely a line moving backward on a map. Flow that had once reached two lakes became concentrated toward one remaining calving front, and this helps explain why scientists watch more than total length. They track width, surface elevation, speed, crevasse density, lake depth, and the position of the front relative to bedrock features, and two glaciers can retreat the same distance while undergoing very different internal changes, which also explains why old maps remain valuable, because Lago Geikie formed only after the glacier withdrew, and images from different decades show the lake lengthening as the terminus migrates inland, and the water is a visible archive of where the ice used to be. But the archive has missing pages, since high-resolution measurements of the bed beneath the lower glacier are difficult to obtain, and temperate ice contains water and fractures that complicate radar surveys. Steep mountains limit access, while clouds often hide the surface from optical satellites. And even lake bathymetry tells scientists only about terrain already uncovered by retreat, not the full shape of the bed still buried under ice. That hidden topography is the largest uncertainty in the answer to what happens next. A deeper basin farther inland could allow the front to remain exposed to strong buoyancy and calving. A shallower ridge could provide temporary stabilization, while a narrowing valley could reduce the width of the calving front, while a widening basin could expose more ice to the lake. And the front is therefore moving through a landscape we cannot yet see completely. The bed sets the pace, and the next major reveal is this. The future of Tyndall may depend less on the size of the iceberg visible today than on the shape of rock kilometers upstream. The most dangerous misunderstanding about glacier calving is that the largest visible break must be the most important event. A wall of ice falling into a lake is spectacular, but scientists are often more concerned with what happens before and after the splash. They ask whether the glacier speeds up, whether the surface lowers, whether the front retreats into deeper water, and whether the remaining ice loses contact with a stabilizing ridge. And those changes determine whether a calving event is an isolated loss or part of a larger dynamic shift. And Tyndall's recent behavior contains signals in both directions. Because the glacier has lost 2.2 kilometers since November 2020. Since November 2020, after a quieter period, its lower surface is deeply fractured, and Lago Geikie has continued to occupy the space left behind. And together, those observations support the title's urgency. At the same time, the 2026 calving was described as incremental compared with the large events in 2023-3, and researchers have not reported the kind of sustained flow acceleration that would justify declaring an imminent wholesale collapse. The most defensible near-term expectation is continued production of many smaller icebergs, with the possibility of more active calving during the next austral autumn. And that is not a weak conclusion. It is a measurable forecast based on the structure of the front. Heavily crevassed ice offers many fracture boundaries, so instead of one clean crack releasing a broad tabular slab, a web of existing fractures can divide the front into smaller blocks. And those blocks detach, the terminus can retreat in steps. Each step changes the stress distribution in the ice that remains. One older analysis of Tyndall found that the glacier bed remained below the lake's outlet elevation for more than 14 kilometers inland, from the position measured around 2000, and that result suggested the physical potential for extensive retreat without predicting when it would occur, while later researchers emphasized that coarse bed maps make long-range projections uncertain. Both statements can be true, and the uncertainty remains. The valley may permit retreat far inland, while ridges, narrowing sections, changing flow, and climate variability alter the pace. And potential describes what the terrain allows, rather than providing a calendar. The glacier's average retreat can be measured in tens of meters per year, yet episodic calving can remove large sections much faster. Its lake can deepen and lengthen gradually, yet the geometry at one critical point may change the dynamics. The front can advance seasonally while the long-term position continues to move inland. Slow change and abrupt events are not opposites here because they are parts of the same system, and the larger southern Patagonian ice field adds another scale since more than 70% of its calving glaciers terminating lakes and lake-terminating glaciers account for a large majority of the ice field's measured mass loss. Patagonia's outlet glaciers are unusually dynamic because the ice is temperate, precipitation is high, slopes can be steep, and many termini meet deep water. Tyndall's not the fastest of them, and that contrast makes it scientifically useful. And if every deep lake produced the same rapid acceleration, the mechanism would be simple. Tyndall's slower response shows that local geometry and flow can restrain a glacier even when parts of its front approach flotation, and it provides a natural comparison with neighbors that have accelerated dramatically after losing contact with the bed. And this is the midpoint reframe. Lago Geikie is growing and Tyndall is losing ice. The unresolved question is whether the glacier will continue a comparatively steady pattern of thinning and episodic calving, or whether its hidden bed will eventually place the front in a configuration where retreat accelerates. And that distinction affects how scientists interpret the future contribution of Patagonia's glaciers to sea level rise. Ice already floating in a lake. does not raise global sea level when it melts in the same direct way as grounded ice entering the ocean system, but the loss of a stabilizing front can allow more grounded ice upstream to flow and thin. And for Tillanes, the pathway is indirect, yet the loss of glacier mass still ultimately changes water storage and contributes to the broader decline of land ice. And Tyndall's measured volume loss was estimated at about 0.79 cubic kilometers per year between 2020, easing to roughly 0.48 cubic kilometers per year between 2012 and 2016. Those values are historical averages, not a current annual forecast, and they show that a glacier can lose substantial volume even during periods when its front position appears less dramatic. Surface lowering is part of that hidden loss because a glacier may thin across a broad area without producing a headline-sized iceberg, and lowering then increases melting because the surface sits in warmer air at lower elevation, a feedback identified in earlier Tyndall research. Meanwhile, calving removes ice directly from the terminus, and the two processes reinforce one another without being identical. Climate influences snowfall and surface melt. Ice dynamics transport mass downhill. Lake water and buoyancy affect the front, and bedrock geometry controls resistance. No single image or temperature measurement explains the entire retreat. Optical satellites reveal the front when clouds allow. Radar can track motion through darkness, and some weather, digital elevation models measure thinning, and bathymetric surveys map the lake floor. Astronaut photographs add high-resolution oblique views that can expose shadows, cliff height, and fracture patterns, and together, those tools turn an inaccessible glacier into a monitored system. Yet monitoring is not prediction in the everyday sense, because scientists can identify conditions that favor calving and can expect seasonal bursts. And they cannot name the exact hour when the next block will fall or guarantee whether the bed ahead will accelerate or slow the retreat. What they can do is watch for a combination of signals: faster flow, rapid surface lowering, wider fractures, a retreat into deeper water, and loss of contact with stabilizing terrain. And if several of those signals strengthen together, the story changes. For now, the bergs in Lago Geki are evidence of active retreat, not proof of an immediate catastrophe. And the glacier is not waiting for one final crack. It is adjusting continuously as ice, water, and rock redistribute forces along the front. The final part of this story begins with that adjustment and asks what the next observations would actually mean. In the months ahead, the easiest change to see will be the number and pattern of icebergs in Lago Geki, where fresh bergs will appear bright against the dark water. Wind and currents will spread them away from the terminus, leaving a temporary trail that shows where calving has been most active. And the more important changes may be harder to see, because scientists will compare the position of the front with the May 2026 image and with satellite scenes collected before and after the 2023 retreat. They will look for sections that have pulled back faster than the rest. And they will measure whether the glacier's narrow lower tongue is becoming shorter, wider, or more fractured. They will also watch the ice upstream, since a calving front can retreat without a major change in speed, as Tyndall has often done. But if surface features begin moving faster toward the lake, that could indicate reduced resistance near the terminus. If the surface lowers rapidly at the same time, the glacier may be stretching and thinning dynamically rather than simply losing blocks at the edge. Another clue will come from the season, because the 2026 astronaut photograph was taken during austral autumn, a period of active calving at Tyndall and some neighboring glaciers. And based on the dense crevasse pattern, scientists expect continued small berg production and have identified the next austral autumn as a period worth watching for another burst. That period is a monitoring window rather than a disaster deadline. No countdown exists. Between now and then, the glacier will keep flowing as snowfall at high elevations will add mass, while melting, runoff, deformation, and calving remove it. And short-term weather can change surface conditions, but the long-term retreat reflects accumulated imbalance and dynamic feedback over many years. The growing lake will remain part of that balance because as Tyndall withdraws, Lago Geki gains length and exposes more of the valley. New bathymetry can reveal whether the glacier has retreated over a ridge or into a deeper basin. That information may be more valuable than the visual size of any single iceberg because it constrains the forces acting beneath the front, and a shallow rise in the bed could slow retreat by increasing contact and resistance. A deepening basin could maintain buoyant conditions and allow the front to remain vulnerable. A narrower channel could reduce the area exposed to calving, while a broad basin could do the opposite. The glacier is effectively conducting a slow survey of its own hidden bed as it retreats. And unfortunately, learning by retreat means the most useful information sometimes arrives only after the ice has uncovered the terrain. Researchers are trying to close that gap with radar, gravity measurements, lake surveys, and models, but Patagonia remains a difficult place to map at high resolution. This uncertainty should shape the language used about Tyndall. There is strong evidence that the glacier has retreated substantially since late 2022. There is strong evidence that it has thinned for decades and that Lago Geki has expanded with the retreat. And there is also direct evidence of active calving in 2026. But there is not strong evidence for an imminent total collapse, a sudden lake outburst, or a specific date when the glacier will cross a point of no return. Those claims would go beyond the observations, and the distinction matters. The defensible warning is more subtle. Tyndall's front is moving through deep water while the glacier remains heavily crevassed and thinner than it was in previous decades. The bed ahead is not mapped well enough to exclude a future acceleration. A new sequence of speed, elevation, and calving measurements could reveal a transition before it becomes obvious in a single photograph. This is why Tyndall matters beyond one remote corner of Torres del Paine. Across the Patagonian icefields, outlet glaciers respond differently to similar regional climate pressure. Some accelerate suddenly when deep basins and buoyancy reduce basal resistance, while others retreat more steadily. Understanding those differences improves estimates of future ice loss, changing freshwater landscapes, and the contribution of mountain glaciers to rising seas. It also corrects a common assumption about climate change, that every consequence unfolds as a smooth line. Glaciers can thin gradually, then lose a large section in days. And they can retreat rapidly and then pause against higher ground, while continuing to flow forward while their visible front moves backward. Their future is shaped by global temperature and precipitation, but expressed through local valleys, lakes, and fractures. Nat Tyndall. The local expression is now unmistakable. A lake that did not exist in its modern form before the 20th century stretches into the mountains. An outlet that once reached a second lake has been severed by thinning. A front that stood more than 2 kilometers farther down valley in late 2022 has pulled back, leaving new water and new bergs behind. The next change will probably not arrive as one cinematic ending. It will arrive as another fracture opening across the lower ice. Another cluster of small bergs appearing on the lake, and another satellite measurement showing the front a little farther inland, and perhaps eventually a shift in speed or geometry that tells scientists the glacier has entered a different phase. That is the real meaning of what happens next. Not a single prediction, but a sequence of tests. And scientists will ask whether the front remains grounded, whether the lake deepens, whether flow accelerates, whether thinning spreads upstream, and whether the next autumn produces only a burst of small bergs or exposes a cleaner fracture capable of releasing a larger slab. Every answer will narrow the range of futures that remain physically plausible. For viewers, the image from space is a warning because it makes retreat visible, and for scientists, it is a baseline. The shadow fixes the height of the cliff, the crevasses record stress, the bergs mark recent breakage, and the lake outlines the glacier's former path. In future photographs will be compared against all of those physical anchors, and somewhere in southern Patagonia, far below the orbiting camera, water will continue touching ice along the front tens of meters high, and cracks will deepen, and blocks will loosen while the glacier moves forward under gravity even as its boundary moves back. A moving river of ice, a growing lake, and beneath them both, a hidden valley deciding the pace.